Welcome to this lecture series in complex numbers. We will continue our discussion from last time and let us recall a few things that we discussed. So we defined complex numbers as ordered pairs of real numbers. So any complex number is of the form a comma b where a and b are reals. And suppose z and w are two complex numbers. Then we defined their addition coordinate wise and their multiplication was defined in a funny way. And in this lecture, why this particular definition was chosen will become clearer. So here is what is called the standard form of complex numbers. So suppose z is some complex number a comma b, then a simple computation will show you that z is actually equal to this complex number, where this is the multiplication of this complex number with that. So if you just follow the definition of the multiplication, you will get that this is equal to that, right? So what we do is we give this guy a special name. This we denote as I, called iota or something. I think this is called iota. Okay, and instead of all these decorations, we just simply write a. So the above thing can be written succinctly as a plus ib. And from now on, instead of writing this for a complex number, we just write that. So this is the standard way to denote a complex number. All right. So let's note a few things. First of all, it's a matter of notation. When we write a, where a is a real number, we mean this complex number. So that's a notational convention. And one can note that if a is a real number and z is a complex number, then az, well, this is also in some sense just notation, so there is nothing to note. So if a is a real and z is a complex number, then az is really this guy, because in place of this, we are writing a. So you can sort of scale a complex number with a real number if you want to think about it that way. This has a very nice geometric meaning. So suppose I have a complex number z. Suppose z is that complex number and a equals 2. Then 2z is nothing but the complex number obtained by scaling this guy by the number 2. So this is 2z. So this is sort of a scaling operation if you want to think about it that way, but this is the formal meaning. All right, so from now on, this will be the way to denote complex numbers. We will no longer use this coordinate pair notation. Okay, so addition and multiplication in this new notation behave in the obvious way. This is equal to a plus c plus I c plus d. What am I writing? A b plus d. Right? And now, for multiplication, well, we already know what that is because we know the formula for multiplication. But for the moment, suppose we multiply these two brackets like we multiply brackets in high school for ordinary algebra. We just multiply this with that, this with that, this with that, and this with that, and add the four things. So what are the four things? The four things are AC plus A into that. So that is nothing but I times AD plus IB into that. So that's IBC plus IB into ID. So that is I square BD. But I square is minus 1 because 0, 1 square is minus 1, 0. Okay, I don't want to... Well, I square is minus 1 basically. That you can see by definition of I. I is 0, 1. And if you just follow the definition of multiplication, you will see that I square is minus 1. Okay, so this is AC minus BD plus IAD plus BC. So that strange looking multiplication is kind of just a matter of opening brackets. The way we did, we have a special symbol for the complex number whose square is minus 1. There are two such complex numbers, I and minus I. When we write I, we mean 0, 1. So that's it. That's why multiplication was chosen in that way. This is one way to answer that question anyway. All right. So let us note this special product, a plus ib times a minus ib. If you compute this, you get a square plus b square. So just remember this. Again, it's a matter of a very simple computation, so you can verify. Okay, let's go ahead. So these are some integral powers of I. I square is minus 1, which is same as saying that 1 upon I is minus I cubed is I square times I, which is minus 1 times I, and hence it is equal to minus I to the 4 is I square times I square, which is minus 1 times minus 1, and hence it is equal to 1. So one can arrange the powers of I on the unit circle. The magnitude of I is 1, and so is the magnitude of I square and I cube and I to the 4 and so on. So all of them lie on the unit circle. Unit circle is basically the set of those complex numbers which are at a unit distance from the origin, whose magnitude or modulus is 1. So the complex numbers, this is 1, this is I square, and this is I cube. And 1 is also equal to I to the 4, and basically it cycles around. This is I to the 5, I to the 6, I to the 7, I to the 8, and it just keeps cycling around. Let us compute this particular complex number. It's a very basic exercise, but let's do it in full. So this is equal to 3 plus I, and here is the trick. We want to remove complex numbers from the denominator. So what we will do is we will multiply and divide by these things. So here ultimately we'll use this fact that a plus ib times a minus ib is a square plus b square. This is what we recorded earlier. So we will just apply that to these two multiplications and these two multiplications. So therefore the numerator is some horrible thing which we can compute. We will do that later. But the denominator is very simple. The denominator is 1 square plus 1 square times 1 square plus 2 square. This 1 square plus 1 square comes from this multiplication, and 1 square plus 2 square comes from that multiplication. So this is equal to, let us multiply these two brackets. So this is 3 plus I times 1 plus 2 plus iota minus 1 plus 2. I hope I'm not making a mistake. Divided by 2 times 5. So this is equal to 3 plus iota. 3 plus iota divided by 10. Maybe I made a mistake. Let me just check my computation. So 1 times 1, and I square is minus 1. There's a minus sign, so I get a 2. That's fine. Minus I times 1 is that minus 1, and 2 times 1. So this much is fine. Yeah, it is fine. So this is equal to 9 plus 3 iota, or 9 minus 1 plus 3 iota, or iota comes out, and we get 3 plus 3 divided by 10, and that is equal to 8 plus 6i by 10, which is 4 by 5 plus 3 by 5i. So it doesn't matter if either you write 6i or i6, it's the same thing. So maybe I'll be more standard. This is i6, but the previous one was also fine. So that's a simple computation. Okay. Now about inverses. We have already seen this in the previous lecture. So I'll just straight away write down. If z is a plus ib, which is non-zero, meaning at least a or b is non-zero, then the inverse of z exists, which means that there is a complex number w such that wz is 1. And that complex number is nothing but a minus ib divided by a square plus b square. Right? So that should be clear by now. Okay, and to remind again, 1 means 1 plus 0, 1 plus I0, or 1 plus 0i, whichever. Okay. So there is also a very nice trigonometric form of a complex number, which just falls out of the standard form, but let's do that in detail. So suppose I have this complex number and assume it is a non-zero complex number. Then one can write z in this following way. This multiplied by so that's a simple trick. And now we can interpret this trigonometrically. So let's say z is this complex number a comma b, and theta is the angle that it makes with the positive x-axis. All right. So then if we take this, this point that you get after projecting z on the x-axis, this would be a, and this is nothing but root of a square plus b square. So this ratio here is cos of theta, and similarly this ratio here is sine of theta. So this is nothing but the modulus of z times cos theta plus I sine theta. So this is one way to represent non-zero complex numbers. It's modulus times cos theta plus I sine theta, where theta is the angle that this line joining the complex number with the origin, makes with the positive direction of the x-axis. And it is not only valid for complex numbers lying in the first quadrant, it is true for any non-zero complex number. You just have to take the angle made by the positive direction of the x-axis. So that's the trigonometric form. And that's it. So as usual, like, comment, share, subscribe. I will see you next time.